Welcome back for Simon's second lecture on scalar curvature rigidity of polytopes. Full screen.
Perfect. Yeah, so in today's lecture, I want to discuss some connections between scalar curvature and global geometry. And so this fits into a larger scheme of sort of how the infinitesimal geometry of a Riemannian manifold, as described by the Riemann curvature tensor, how that affects the global shape and the topology of a manifold. And so there are many results in geometry that link curvature assumptions on the one hand to geometric or topological conclusions. And what I want to focus on today is a class of results that have to do where the assumption concerns the scalar curvature. So this is of interest for several reasons. One of them being that scalar curvature is the weakest of all the curvature quantities you can consider. So it contains less information than the Ricci curvature or the full Riemann curvature tensor. And that means there are relatively few techniques that are capable of detecting and exploiting scalar curvature assumptions. A second reason is that positive scalar curvature manifolds come up in connection with relativity. When you look at Cauchy data in relativity, in other words, you have a space-like hypersurface sitting inside an ambient Lorentzian manifold, which satisfies the dominant energy condition, for example. Yes, so one of the earliest results in this direction is the result of Shane and Yao on the positive mass theorem. And so here, the setting is that in the simplest case, you have a metric on Euclidean space Rn. So you just take Rn, but the metric G is not a Euclidean metric. And let's assume that the metric is asymptotic to the Euclidean one. So Gij is equal to delta Ij plus a small error term. And here the dimension is at least 3. And we want the decay to be faster than r to the 2 minus n. So then under that condition, if the metric has non-negative scalar curvature and has this decay, then it follows that the metric has to be flat. So in other words, it's not possible to deform the Euclidean metric on Rn, for example, in a compactly supported way, so that the scalar curvature remains non-negative. At least there are no non-trivial perturbations of that type.
Excuse me.
This is proved by Shane and Yao up to dimension 7 and by Witten in all dimensions. This result is not the most general version of the positive mass theorem. You can more generally look at manifolds that are asymptotically flat, but not necessarily diffeomorphic to Rn. But let me not go into that.
Excuse me?
There's a closely related theorem, which was conjectured originally by Dirac and also proved by Shane and Yao up to dimension 7. And this was proved by Gromov and Larson in all dimensions. So what it says is that if you consider any Riemannian metric on the torus Tn, so you take a Cartesian product of a circle with itself n times, and if you have any Riemannian metric on this torus with non-negative scalar curvature, then the metric has to be flat. So this means you can never have positive scalar curvature. And even non-negative scalar curvature, the borderline case, this is only possible if the metric is flat. Now, an interesting aspect of these results is that they involve, that you can draw a conclusion based on an assumption that has to do with the lower bound on scalar curvature. You can also ask the question, what happens if you impose an upper bound on scalar curvature? And the answer to that is, this doesn't really let you conclude anything. So it was shown by Locamp that if you give me any compact manifold, there's always a metric with negative scalar curvature, even negative Ricci curvature. And in fact, these metrics are dense in a sufficiently weak topology. So this means generally speaking, negative scalar curvature and negative Ricci curvature metrics, they exist in abundance. And if you have an assumption that your metric has negative scalar or Ricci curvature, that will not tell you much. So this makes it all the more remarkable that positivity is much more rigid, and that there are obstructions to the existence of positive curvature metrics, positive scalar curvature metrics, that is. Okay, so these are two very classical results, two landmark results on positive scalar curvature. Now here, in a way, what you do is you have a comparison term where you compare to a flat metric. So in the first result, you compare to the flat metric on Rn. In the second case, you compare to the flat metric on a torus. Now, there are other results that involve comparisons with other model metrics. So for example, you can compare to a round sphere. And so in that case, there's a rigidity result due to Laroux. So what he proved is that if you have any metric on Sn, which has scalar curvature at least n times n minus 1. Now n times n minus 1, that's the value of the scalar curvature of the round metric on Sn. So the assumption is that the given metric has at least as much scalar curvature as the standard metric. Now that by itself will not imply rigidity, because if you take a round metric on the sphere, you can always generate more curvature by simply scaling it down. So you can look at a scaled down version of the round metric and it will have more curvature. So what Laroux did is he put in an extra assumption that the metric G is bounded from below by the standard metric on Sn. So put another way, if you take any curve in the sphere and you measure its length with respect to the given metric G, then the length with respect to G should be greater or equal to the length with respect to the round metric G zero. Now, under that assumption, you can draw the conclusion that then the two metrics are equal. So the round metric, so the metric G has to be equal to the round metric. Now, there are two types of techniques that mathematicians have developed to deal with this type of problem. And so one is based on spin geometry. It's based on Dirac operators, and that approach was pioneered by Witten, and this is later used in the work of Gromov and Larson, and also in the work of Laroux. There's another approach which is based on minimal surfaces, and this is the original approach of Shane and Yao in dimension 3, and then you can extend it to higher dimensions. And in that case, you would look at minimal slicings, which means you have an n-dimensional manifold, and you find yourself a minimal surface of dimension n-1 sitting in the n manifold, and then you look at a variational problem within the minimal surface, and then you look at another minimization problem in that new surface, and so on. And so in that way, you can create higher dimensions. Now, I should say that the approach is limited to dimension at most 7 because of the presence of singularities in hypersurfaces. Types of techniques, one based on spinors and Dirac operators, and the other one based on minimal hypersurfaces and minimal slicings. Now today I want to address a variant of these problems, which is concerned with the rigidity of polytopes. So this is a problem that Gromov posed some years ago. And so he assumed that you have a metric on a polytope. So just look at maybe a convex polytope in Rn, and then assume that we have a Riemannian metric. And let's assume that the scalar curvature is nonnegative inside the polytope. Now, because now we have a manifold with boundary, you have to impose a an assumption concerning the boundary behavior of the metric if you want to prove rigidity. And so what Gromov proposed to do is to put in an assumption that the boundary faces have non-negative mean curvature with respect to G. So in other words, if you take like the sum of the principal curvatures, that would give you the mean curvature, and you want that to be non-negative. Now, this mean curvature, this is computed with respect to G, and this is a very natural assumption because in a way, mean curvature is the sort of can be viewed as a distributional version of scalar curvature. And so in that sense, it fits together nicely with the scalar curvature assumption in the inside. And then Gromov proposed making another assumption concerning the dihedral angles. So if you have like two faces that have at least a point in common, then you want to assume that the dihedral angles computed with respect to G are smaller, that is to say more acute, than the dihedral angles with respect to the Euclidean metric. So we have kind of these two spaces, the polytope equipped with the G metric and the polytope equipped with the Euclidean metric. And we want the polytope equipped with the G metric to have more scalar curvature in the inside, more mean curvature at the boundary, and we want the angles to be more acute. So then under these assumptions, the conclusion is that the metric should be flat. So it should be rigid. Now, this result was proved by Gromov himself in the special case of cubes. And he did it by a reduction to these earlier rigidity results. So you can do a reflection and then you can reduce it to the existing results. There's a beautiful result by Chao Li, where he verified this conjecture for prisms in 3D. And then he has a higher dimensional result, where he considers higher dimensional prisms. But in higher dimensions, he needs to assume equality of angles. So the original conjecture assumes inequality of angles, but then under an assumption of equality, Chao Li was able to prove it in higher dimensions for prisms. There's also work by Wang, Xi, and Yu, and where they claim to prove the conjecture in all cases, and this is subject to verification. Yes, so the result I want to discuss today is a partial result which verifies this conjecture of Gromov under a slightly stronger assumption on the angles. Namely, I want to assume that I have a metric on a polytope such that the scalar curvature is non-negative in the inside, the mean curvature is non-negative on the boundary, and then I want to assume that the angles computed with respect to G are equal to the angles computed with respect to the Euclidean metric. So instead of inequality of angles, I'm assuming equality of angles. Right, so under these assumptions, I can show that the metric G is flat and the boundary faces are totally geodesic. Okay, so let me tell you the essential ingredients in the proof of this result. So essentially, all the work on this problem, again, uses either spinors or Dirac, or uses minimal hypersurfaces. So for example, the work of Chao Li uses a generalization of minimal surfaces. It uses capillary surfaces in a very interesting way. Now, this argument that I'm using, this is based on spinors. And so it involves, first of all, a couple of reductions. The first reduction is that it's enough to consider the odd-dimensional case. It's because if you can handle odd dimensions, then to handle even dimensions, you just look at a Cartesian product with an interval, and then you apply the result one dimension higher, and then that will imply the conjecture one dimension in the original dimension. Right. Now, the parity of the dimension, this if you use minimal hypersurfaces, that doesn't play a big role. But in Dirac operators, it does make a difference, and I will explain in a minute where the oddness of the dimension plays a role. Okay, so then the second step is we want to solve the Dirac equation on this polytope. And so first of all, one has to look at a modification of the Dirac operator on like where you use a twisting bundle. But then the second issue is that we want to solve this on this polytope, which is a singular domain. And so that means the standard results on existence and Fredholm property, existence theory for Dirac operators on manifolds with boundary, you can directly apply that since you're dealing with a singular object. And so to get around that, what you can do is you can approximate your given polytope by a sequence of smooth domains. And so, for example, you can exhaust it from the inside by a sequence of smooth domains. And then on each of these approximating domains, you can consider a Dirac operator. And specifically, I want to consider a Dirac operator for an M tuple of spinors, and I want to impose a boundary condition. Now, the reason I want to look at M tuples of spinors, this is so that I can make sense of the boundary condition. So I'll explain that in a minute. But the important point is then that the boundary condition is elliptic in the sense of Lopatinsky-Shapiro. So it's a nice elliptic boundary condition. And so then the Dirac operator with this boundary condition has a Fredholm property, and you can compute its index. Right. Now, this is where the parity of the dimension comes in. So it turns out that if you set up this boundary problem for the Dirac operator, then the index is equal to 0 in even dimensions, and it's equal to 1 in odd dimensions. And so then if you're in odd dimensions, because the index is 1, you can conclude that the operator has non-trivial kernel, because the dimension of the kernel exceeds the dimension of the co-kernel. And so then from that point on, then you can mimic like the classical Dirac operator results in the theory of positive scalar curvature. So what you do is you consider an element in the kernel, and then you plug that into a Weizenburg formula and you integrate. And then in the very end, then because you can do that on any of the approximating domains, then the idea is to pass to the limit. Because in the end, we really want to solve an equation on the singular space, on the polytope, and the approximating domains. That's just a tool that helps us solve that problem. So that's why in the end, we want to pass to the limit. Okay, so let me go into more detail. So the first step is I should tell you about the specific boundary problem I'm considering. So let's assume that we're in dimension n, and n is odd. And let's assume now that omega is a smooth convex domain in Rn with boundary sigma. And let's assume that we have a metric on that domain, on that smooth domain. And so in addition to a metric, I need a map n from the boundary to the sphere. So the simplest example would be that G is the Euclidean metric, and this n is the Gauss map of my smooth domain. So it would in the simplest case, you could just define n to be the unit normal, and that will give you a map to the unit sphere as n-1. Okay, and so then let's define delta n to be the space of spinors on Rn. So this is a finite dimensional vector space. The dimension is 2 to the integer part of n/2. And then let's say we pick an orthonormal basis, and then we can consider these matrices omega 1 to omega n. And here they're given by Clifford multiplication of like vectors in the standard basis of Rn, and then you take the Clifford product with the elements of the orthonormal basis of spinors. So basically these omega 1 to omega n, these are matrices that satisfy these Clifford relations. So you take omega A and you multiply with omega B plus omega B times omega A, that will give you minus twice delta AB times the identity. And the omega 1 to omega n are like complex n by n matrices. And so basically this power 2 to the n over 2, this comes in because this is the smallest dimension n where you can find matrices with these algebraic relations. All right, so these are called the Dirac matrices. Now, let's consider the spinor bundle with respect to the metric G, and we can consider elements of this bundle where you take a direct sum of the spinor bundle S with itself m times. So the elements are m tuples of spinors, and so now I can define my boundary condition. So the boundary condition will be defined in terms of this boundary now, chi. So yeah, so this is called a boundary chirality. And what it does is it maps a section of this bundle E restricted to the boundary, and it produces another section of the same bundle. So you have basically these, a set of spinors S1 to Sn defined on the boundary, and then you map that to a new section chi S. And this S, this is a section of E restricted to the boundary. And so then the way this chi ends is basically it does two things at the same time. So the first thing is we take the unit normal to the hypersurface with respect to G, and then we take a Clifford product of nu with each vector. And then the second thing is we take linear combinations using these Pauli matrices or Dirac matrices omega 1 to omega n, and we use this map capital N to form these linear combinations. And so then this chi, this is what we call a chirality, so it's self-adjoint, and it has the property that chi squared is the identity. So this means the bundle then breaks up into the plus and minus eigenspaces, and so then you can use that to formulate a boundary problem, namely, if you have an m tuple of spinors, we want to solve the Dirac equation in the inside, and we want to impose the condition that the restriction of S to the boundary lies, let's say, in the +1 eigenspace of this boundary chirality chi. So the point here is that if you solve a second order PDE such as the Laplace equation, then you can impose a Dirichlet boundary condition and you can prescribe all the boundary data. However, the Dirac equation is first order, and so then that means you only get to prescribe half of the boundary data. And so then the way you would think of this in this setting is that for any m tuple of spinors S, you can restrict it to the boundary, and then it breaks up into these two subbundles given by the +1 and -1 eigenspaces of this chirality chi. And so then you can basically prescribe the projection to one of these subbundles, but not to the other. Yes, so this is the boundary problem. And now the model case would be the case when G is the Euclidean metric and this N happens to be the Gauss map. So then like there's no difference between n and u. And so then the point is, in this case, the boundary condition is set up so that if you take an M tuple of parallel spinors, of constant spinors on Rn, then this will satisfy the boundary condition. So essentially, the boundary condition is kind of reverse engineered so that this M tuple of constant spinors in the model case would satisfy the boundary condition. So this is the boundary problem. And so then, well, you have to check that this gives you an elliptic PDE. And well, this has to do with the properties of this boundary chirality. So you can check that it's self-adjoint, that its square is the identity. And then the important thing is that Clifford multiplication by tangential vectors anti-commutes with chi. And so that implies that it gives you an elliptic boundary condition. And this is it's called a chiral boundary condition. So for Dirac operators, you can prescribe different boundary conditions. So some are non-local, like the Atiyah-Patodi-Singer boundary condition. This one here, this is a local boundary condition. Now, the next step is there's a dual boundary condition. So the Dirac operator, this is formally self-adjoint, but the boundary condition makes it the operator non-self-adjoint. And so the adjoint would be given by this dual boundary condition where you project to the other eigenspace. So kind of the dual problem would be to solve the Dirac equation in the inside, but now with the boundary condition that the restriction to the boundary lies in the negative one eigenspace. And so then it would give you the boundary condition chi s equal to negative s. Right, and so then if you look at the special case when G is Euclidean and the map N is the Gauss map of the hypersurface sigma, then what would happen is that if you take in the boundary condition, if you take the plus sign, that would have one-dimensional kernel, and the kernel would consist of parallel spinors. And then if you take the dual boundary condition, then the kernel would be trivial. And so then that would give you a Fredholm index of 1. Now in the even case, in the model case, the kernel and co-kernel would both be one-dimensional, and then the Fredholm index would be 0. So the point is that in the model case, you can just work out what the kernel is and what the co-kernel is, and that lets you compute the Fredholm index. Another way of doing it would be to use index theory. So for example, there's a holographic index term, and that lets you compute the Fredholm index in greater generality. But at least in this case, you can just compute it using deformation invariance based on the study of the model case. And so the important point is, if you have an arbitrary metric and you have an arbitrary map N, then as long as it's homotopic to the Gauss map, then the Fredholm index is 1, because you can deform it to the model case. In general, what would happen is that the Fredholm index would have to do with the degree of the map N, and this is what you get if you use index theory. All right. So now in particular, once you know that the index is 1, that means the kernel is non-trivial. And so then you can plug an element of the kernel into a Bochner formula. Now, in this case, this requires some additional calculations because basically you have a boundary condition and the boundary condition depends on the map N. So then if you plug a section of this bundle into the Weizenburg formula and integrate, you get boundary terms. And here's how they look like. So basically in the formula, you have a term in the inside that involves an L2 norm of the covariant derivative of this n tuple of spinors. Then there's a scalar curvature term in the inside 1/4 times scalar curvature times the squared norm of the spinor. And of course, this is the whole point why spinors are useful in the study of scalar curvature, because this integral formula, it doesn't involve Ricci curvature or Riemann curvature. So if you have an assumption on the scalar curvature, that's good enough to apply this formula. And then here, the last term on the left-hand side, that's a boundary term, a boundary integral, which involves a difference of two quantities. The first one is the mean curvature of the boundary, and the second one, this is the norm of the differential of n. And yeah, let me tell you what I mean by this norm. So this n, this maps the boundary to Sn minus 1, and then this Dn, this is the differential that maps the tangent space at a point x on the boundary to the tangent space at the image point n of x to the sphere. And then the norm of Dn, this is interpreted as the trace norm, or the sum of the principal, sum of the singular values. Right? So you just sum up the singular values, and that gives you a norm of a linear transformation, which is called the trace norm. And so then the term that comes in is exactly the difference between the mean curvature and the trace norm of the map. Now let's turn to the right-hand side. So on the right-hand side, you get the L2 norm squared of the Dirac operator applied to S. And then you get boundary terms, which involve the boundary Dirac operator d sigma. And then they involve the difference of S and chi-S, where chi is this chirality operator. And so the important point here is that if this lies in the kernel, so if it satisfies the Dirac equation subject to this chiral boundary condition, then all the terms on the right-hand side vanish. I mean, the interior term vanishes if S solves the Dirac equation. And then if S equals chi-S, then the boundary terms on the right-hand side go away. Now, the model case, again, would be when G is Euclidean and N is the Gauss map. Now, in this special case, here's what would happen. So in this case, the mean curvature, this is the sum of the principal curvatures, but the principal curvatures for a convex domain, they're the same as the singular values of the differential of the Gauss map. So in that case, H equals the trace norm of Dn. And so then in this special case, in the model case, what would happen is the solution of the PDE, the element of the kernel, that would be parallel, and then each term would vanish. So S would be parallel, and the scalar curvature would be 0, and H minus norm Dn would vanish as well. And so in particular, what this tells you is that you get a rigidity form for a smooth domain if you assume the scalar curvature is non-negative in the inside, and this H minus norm Dn term is non-negative on the boundary. So put another way, kind of, if you have a smooth convex domain, then it's rigid sort of within the class of metrics with these properties that the scalar curvature is non-negative and the mean curvature is at least the norm of Dn. Okay, so this is basically what you can do for a smooth domain. Now let's go back to the problem of polytopes. So let's assume now that omega is a convex polytope. So then it's an intersection of half spaces. So I can write it as I can write each half space in the form ui less than or equal to 0, where ui is a finite collection of linear functions. And then like the ni, they would be like the unit normals basically to these boundary faces computed with respect to the Euclidean metric. So then what we want to do is we want to approximate this polytope by smooth domains. And there are many ways to do that. I mean, you can do it by hand. And if you do it by hand, there are various ways to do it. Or you could try to use mean curvature flow. So there's not one canonical, not one unique way of doing it. So one way that you can do this is, and this is something very simple and explicit, is you can look at the sublevel sets of the sum of e to the lambda ui. So you look at the set where the sum is less than or equal to 1. And so then this is a sublevel set of a convex function. So it gives a convex domain. It's smaller than omega. It sits in the interior of omega. And then these omega lambda, they form a nested family of sets, and their union is the interior of omega. So basically they form an exhaustion of this polytope by convex smooth domains. And then I will denote the boundary by sigma sub lambda. And this is now a smooth hypersurface. Okay. And so now let's assume we have a Riemannian metric on our polytope. And let's look at the unit normals to all the faces. And let me call these nu I. And of course, nu I changes from point to point because it depends on the metric G. And so then what you can do is you can compute the normal to this smooth domain in terms of the normals to the boundary faces of the original polytope. And you get like this kind of formula where you basically have a linear combination of the nu I with certain weights. And so now what I want to do is I want to solve on each domain omega lambda the Dirac equation with a chiral boundary condition and then pass to the limit. Now to formulate the boundary condition, I need a map from the boundary to the unit sphere. And so this means I can make a choice here of what map I want to use. And the way I define the map is basically I mimic the formula for the normal and I replace, so I have a linear combination of these nu i's, the normals with respect to G, and basically I just replace every nu I by an ni. And so I mimic the formula for the normal, and then I use that to define the map. And so the motivation is that if you look at the model case, when G is the Euclidean metric, then the nu i's coincide with the ni, and then this capital N reduces to the Gauss map. So basically, I'm cooking up this map in such a way that in the model case, it reduces to the Gauss map. Okay, and so then, well, this is homotopic to the actual Gauss map of sigma lambda, which means I can solve the Dirac equation subject to the boundary condition given by this map. And so then let's take some sequence lambda L going to infinity so that we have a sequence of domains. And then for each L, I can solve the PDE where the boundary condition is given in terms of the chirality that's given by this map N. Okay, so then I get a solution, and then I can plug it into the integral formula, and I get an inequality of this type, where on the left I have the L2 norm of the covariant derivative of S plus the scalar curvature term, and on the right I have this boundary term having to do with the mean curvature and the norm of the N. And let me call this difference B sub lambda L. So that this would represent the difference between these two terms. Now, if this V is non-negative, then you're basically done, because then the left-hand side of the inequality is not clearly non-negative. And so then if you can say that the right-hand side is less than or equal to 0, then you're done and you get rigidity. So this means ideally, you would like to do the smoothing in such a way that is H minus norm dn is non-negative. And so then the question is basically, is the condition on the angles enough to ensure that this quantity is non-negative. Now, unfortunately, it seems that this is not the case. So it seems that this V, this difference, you cannot make it non-negative, or at least if you attempt to do it, it runs into problems. However, what you can show is that this term V lambda L, that it's non-negative, sort of to leading order. So you can show that the dominant contributions have a good sign, and then the error terms that come from the smoothing that may have an unfavorable sign, but you can show that they're small. And so to make this rigorous, what you can do is you can look at the negative part of V, that is to say the maximum of negative V and 0, and then you can argue that this bare term is small in a suitable sense. And so then you have to be precise in what sense you want this to be small. And it turns out that a good way of measuring the norm of this error term, of this bare term, is in terms of a Mori norm. So here's a precise statement. So let's fix an exponent sigma between 1 and 3/2. Now, the 3/2 is not important. All we care about is that sigma is slightly larger than 1. And so then let's assume that the boundary faces are mean convex and that the dihedral angles equal those in the model case. Then let's look at this quantity V, which is the difference of H and norm dn. And so then what you can show is that this Mori norm will go to 0 as L goes to infinity. So you take kind of an L sigma norm, but then you take it over ball R, and then you multiply by a power of R, and then you take the supremum over all R. So that gives you a Mori norm. And you can show that this Mori norm goes to 0. Now, the proof is somewhat tedious because you have to break up the integral into integrals over various regions, and then you can deal with them separately. And essentially what you do is, first of all, you can show that, well, you have this scale lambda, which gives you the smoothing scale. So lambda is a large parameter, and basically the length scale of the smoothing is 1 over lambda. And so now if this R is bounded by a constant over lambda, if it's not too big relative to 1 over lambda, then you can show that this integral is small, because you can just estimate the negative part of V in subnorm by little O of lambda. And so then on these scales, you can show that the integral is small. And then the second case is when the radius R of your ball is much bigger than 1 over lambda, so it's much bigger than the smoothing scale. And in that case, well, the way to do it is to break up basically the region into 3 subregions, where you have one region that contains points that are close to one of the faces, but stay away from edges. And then you have a second region consisting of points that are close to an edge, but that stay away from the n-3 skeleton. And then you have a third region, like having to do with the n-3 skeleton. And then you can show that in each of these regions, you get a small contribution. Okay, so this is just kind of to make precise the statement that this V is almost non-negative. So its negative part is small, and this estimate makes it precise. All right, so now how do we go from there? So remember, in the integral formula, let me go back here, we have a good term on the left-hand side, which has which is non-negative, and on the right-hand side, we have this term involving V, which has an ambiguous sign. So now the point is, assuming that this V is small, you can argue that the right-hand side, maybe it doesn't have a good sign, but at least it's small. And so this uses an estimate in harmonic analysis that was proved by Charlie Fefferman and Phong some 40 years ago. And here's what it says. So assuming you have a potential which has small Mori norm, then you can control the integral of the potential times norm s squared, basically by a small number times the h1 norm of s. Now, there are a couple of caveats in applying this formula. So first of all, Fefferman and Phong looked at this estimate on all of Rn, or on a half space. And so here, you need a boundary version of the estimate, where you have a potential that lives on the boundary of a domain, whereas in their case, they have a potential that lives in the interior of a domain. But it turns out that this doesn't make a huge difference, and the argument can be adapted. The second thing is that even if you can prove such an estimate on a domain, then here you have to be careful, because you have not one fixed domain, but rather you have a sequence of domains that converges to this polytope. And so then you have to make sure that the constant in the estimate doesn't deteriorate as you send lambda to infinity. But that can be handled because all these domains, it turns out that they're by Lipschitz equivalent to a ball. And so then you can apply the estimate on a ball, the Fefferman and Phong estimate, where it holds with some fixed constant, and then you can convert it back to the domain omega lambda. But since it's by Lipschitz equivalent with uniform constants, you lose at most the bounding factor. And so that's how you can apply it on these domains omega lambda L, and then you get this estimate. And so then if you plug it, if you combine it with the integral formula, then from there you can basically finish the argument, because you have these two inequalities. So the first one says that this good term is bounded basically by this boundary term involving h minus norm dn, and then the estimate of Fefferman and Phong tells you that this term is small compared to the h1 norm of s. And so then if the scalar curvature is strictly positive, if it's bounded below by a positive constant, then these two things are in contradiction. I mean, if L is large, then they would tell you that SL has to vanish identically, which is contrary to the assumption. And so in particular, then that tells you cannot have strictly positive scalar curvature. And if the scalar curvature is merely non-negative, in that case, you have to run a little harder, but what you can do is you can pass to a limit, and then you can show that you get a set of m-parallel spinors in the limit, and then you can also show that the matrix given by the inner products of these, that this is a constant multiple of the identity. So then up to some factor, you get an orthonormal basis of parallel spinors, and then that implies flatness, and you can get you can also conclude that the faces are totally geodesic, which finishes the proof. Now, maybe in the last 1 or 2 minutes, let me tell you about the Fefferman and Phong estimate, since this plays an absolutely central role. So to state it, this estimate, let's consider a half space. And let's consider the collection Q of all dyadic n-1 dimensional cubes sitting in the boundary of that half space. So we have this n-1 dimensional hyperplane, and then we look at dyadic cubes sitting in there. Right, now what Fefferman and Phong essentially, or what the analog of their estimate in this setting tells us is that if you have a potential that's defined on the boundary and is non-negative, and if it has Mori norm at most 1, in the sense that these integrals over cubes satisfy this estimate, for every n-1 dimensional cube. Then, if you have any smooth function on the half space, then you get this estimate where you can estimate a potential term in terms of basically an H1 Sobolev norm over the inside. And so here you have a boundary integral on the left, and you have an integral over the inside of the H1 norm on the right. And yeah, so this is exactly then the ingredient you need. And the proof of this estimate is quite sophisticated. I mean, it uses Calderon-Zygmunt decompositions and all these classical techniques in harmonic analysis. All right, so let me stop here. Thank you very much.
Any questions?
Silly question. So the usual Yamaha problem when us with manifold, you make the scalar curvature constant, right?
That's correct.
If you have manifold with boundary, you maybe make the scalar curvature inside constant and then in curvature with boundary constant or something like that. Now, suppose you have a polytope, right? So you have some two-dimensional one things intersecting. So what should be how one would formulate the Yamaha problem? Polytope.
That's a good question. I mean, the condition on the angles, that would be conformally invariant. So this means you could say, well, I haven't thought about it, but off the top of my head, the way I would set it up is in terms of a variational principle, where you look at basically the integral of scalar curvature over the inside, subject to a volume constraint, and you would fix the conformal class. And then if you minimize that would give you constant scalar curvature in the inside and zero mean curvature on the boundary. And then presumably you can tweak that to make the mean curvature constant on the boundary and maybe the scalar curvature constant in the inside. I think that. So my guess is that there wouldn't be that much difference in the case of polytopes.
So another just very simple remark. So one, like, so scalar curvature negative, right? It's a huge set of metrics. So
That's correct.
So one little marker which you can sort of try to use to keep track is take something like from Laplace or something elaborator, count negative eigenvalues. Then if you don't have any, then it's positive scalar curvature. And then if you have some, then that sort of tells you, I don't know how deep you are in the ocean or something like that.
Yes, so I know that you can detect whether, like, your Yamaha metric will have constant positive or constant negative curvature or scalar curvature equal to zero. You can detect that by an eigenvalue.
Right. But if you just count how many negative days you have, that's also a conformal invariant, which gives you you can distinguish among the negative.
Yeah, that's a really interesting point. I mean, in the negative, yeah, there's also the issue, but that arises in the positive case, that the Yamaha problem has multiple solutions. And so then you can have ones with higher energy, and you could keep these apart, like by energy level or possibly by Morse index in that way.
So what happened for the it seems that the estimate of equal angle they are used in order to control the Moreno-Morris potential?
Exactly. So that's an interesting point which I haven't had time to address in detail. So the point is, we want to make the negative part of the potential small, and there are these different regimes, and basically, if you have just inequalities rather than equalities, much of it goes through, but you run into problems in the corners. Now, one can hope that the corners shouldn't matter because the high codimension, but that I haven't been able to make a rigorous argument along those lines. And it's also not completely clear if such a strategy can work. And to explain why, let me go back to this estimate here. I mean, basically you want to estimate this kind of bare term. Now, if you knew that the solutions SL, let's say if they were bounded in soup norm, then you could say, well, the corners don't matter because they're higher codimension. However, a priori, you have no idea like how the L2 norm of this SL is distributed. So if you get very unlucky, it could all kind of concentrate in the corners. And then it could happen that even though the corners are a small set, that if the norm of S concentrates there, then what happens at the corners could become very important. And so it's not clear if one can make an argument that the corners don't matter. At this point, it looks like they do matter. And if they matter, then it becomes complicated because you could have many bases coming together and then they interact in complicated ways.
Yeah, because Fefferman and Phong estimate is valid for all functions, or whereas you want to have it only for solutions of spinor equation.
Exactly. So the Fefferman and Phong estimate works for any function, and that's its strength. I don't need to know any special properties of this S to get my estimate. Now, if there's a way, if I knew more about S, then I would need a weaker estimate, and then it would be the problem would become much easier.
Yes.
Because the main thing you want to control is that the topological H minus of the trace of dA.
Exactly.
Because we probably already saw that because the approximation you wrote down is just to pick this exponential of lambda EI.
Exactly.
I wonder if you probably already considered if you use certain flow will help.
Yes, I mean, one idea would be to use mean curvature flow. And so that leads to an interesting sort of couple problem because you would not just evolve the surface, but you would also evolve the map N. And so then the natural thing would be to evolve sigma by mean curvature flow and N by harmonic map heat flow into the sphere. And when I looked at it, I tried to show that the positivity of H minus norm dN is preserved. So I was trying to show that this is a natural class of objects, but it looks like it's not preserved. And so that suggests that that approach may not work that well. But it's possible that something more nonlinear might have better properties, especially since here we're in the class of convex hypersurfaces. So that gives more possibilities in terms of flows.
Any other questions? And in the out there in the ether?